Application of Water Quality Index to assess the potability of some domestic water supply sources in Mubi North, Nigeria. Abstract: This study set out to determine the potability of some common domestic water supply sources in Mubi North using Water Quality Index, WQI. Two major wards were selected, Barama/Gipalma and Barama, from where a total of 17 samples were collected monthly over a period of 3 months and analyzed for temperature, turbidity, pH, total dissolved solids, TDS, electrical conductivity, EC, total hardness, TH, magnesium, plus, calcium, plus, nitrates, sulphates, phosphate, chlorides, dissolved oxygen, DO, and biochemical oxygen demand, BOD. Standards for drinking water quality as recommended by the World Health Organization, WHO, and Nigeria Industrial Standard, NIS, were adopted for reference. The weighted arithmetic water quality index, VAQI, method was used to evaluate the WQI. Physicochemical analysis showed that the pH, TH, plus, DO, and BOD for all samples in both Barama/Gipalma and Lokiwa met the limits of acceptability set by WHO and NIS. Turbidity and EC failed for open wells and river points in all locations, while TDS and plus met the standards in boreholes and open wells but failed in all river samples. Values as analyzed were all within permissible limit for all samples except River Mudjero, which recorded a mean of 6.25 mg/L as against the 5 mg/L stipulated by WHO. The concentrations of in all samples failed the maximum permissible value stipulated by NIS except for the borehole in Barama/Gipalma. WQI determined that borehole waters from both Barama/Gipalma and Lokiwa are of good quality, WQI equals 45 and 31 respectively. Open wells in Barama/Gipalma are of poor quality, WQI equals 70, while those in Lokiwa are of very poor quality, WQI equals 78. Finally, the river waters from both River Mudjero and Yedzaram were found to be unsuitable for drinking, WQI equals 123 and 116 respectively. Keywords: Water Quality Index, Drinking Water Quality, Assessment of Water Quality, Groundwater, Surface Water, Mubi. Introduction. The rapid increase in population, urbanization, intense agricultural activities and accelerated industrialization in many parts of the world has put a tremendous burden on global fresh water supply, Abasnia et al., 2019, Yisa, Jima, and Oyebo, 2012. With the world's population projected to exceed 9 billion by 2050, United Nations, 2019, access to adequate fresh water supply for, especially domestic and agricultural purposes, will become more difficult except proper water resources management decisions and planning strategies are taken and implemented. In fact, the challenge is not just poor access to fresh water, but also to other environmental resources such as clean air, land, and food. These resources would become even more difficult to access as population and the pollution it inevitably engenders impacts on the environment. In order to guarantee public health, access to adequate water of good quality must be given to the people. However, with the current global economic challenges, governments have been unable to put in place, and where available, unable to maintain working municipal water supply systems in most developing countries of the world. The cost of installing these municipal water supply systems has prohibited their provision even by the governments of some economically well-to-do countries, Colombo and Carney, 2002. Consequently, the inability of the governments to provide adequate supplies of pipe-borne waters through municipality networks has forced the people to resort to obtaining supply mainly from simple traditional sources. These sources are typically open wells, boreholes, streams, ponds, rivers, and direct collection from rainwater. Often, the waters collected from such sources are utilized with inadequate treatment or totally without treatment. Unfortunately, all of these sources are susceptible to pollution and contamination from both natural and anthropogenic influences. For this reason, regular monitoring of the quality of the water resources of such areas are therefore absolutely necessary in order to protect environmental health. Hence, assessment and evaluation of the quality status of the major domestic water supply sources in Mubi becomes important. Assessment of water quality has been established to be a complex process undertaking multiple parameters capable of causing various stresses on the overall quality. A. H. Fathi, F. Abdelhamid, A. Shreda, A. Mohammed, and G. Elgazar, 2012. Traditionally, Approaches to assessing water quality are based on the comparison of experimentally determined parameter values with existing guidelines. But it is always a difficult task to evaluate water quality from a large number of samples, each containing concentrations for many parameters. Therefore, Water Quality Index, WQI, a technique that would provide the composite influence of individual water quality parameters on the overall quality of water for human consumption from a study involving a large number of samples was developed. It became an invaluable tool that could be used to minimize the data volume to a great extent and simplify the expression of water quality status. Tirkepunam, Bhattacharya and Chakraborty Sukalian, 2015, Yisa et al., 2012. WQI is defined as a rating that reflects the composite influence of different water quality parameters determined from the point of view of the suitability of water for human consumption. Chorsia et al., 2018, Haladar, Numanbath, and Farouk, 2017. It can be evaluated on the basis of various physical, chemical, and bacteriological parameters, thus enhancing its versatility as a tool. Tirkepunam et al., 2015. This study therefore seeks to employ the use of Water Quality Index to assess the quality status of some physicochemical water quality parameters in some common sources of domestic water supply in Mubi using the WQI approach. Materials and methods. Description of the study area. Mubi is the capital of Mubi North and it is the largest town in the northern senatorial zone of Adamawa State, Nigeria. It is geographically situated on latitude 10°1130 to 10°2230 and longitude 13°1300 to 13°3000, covering a total land mass of 506.42 Martins and Gadiga, 2015, Wante and Inalifo, 2014. It lies on the west bank of the Yedzaram River and the western flanks of the Mandara Mountains. River Yedzaram flows northward from its source at the Hudu Hills southeast of Mubi, receiving flow from River Mudra at Dijal and draining into the Lake Chad after about 330 kilometers. Wante and Inalifo, 2014 cited Abia, 2004. Mubi has a climate classified as equatorial savanna with dry winter or tropical rainy according to Köppen's code, Kotek, Griesier, Beck, Rudolph, and Rubel, 2006. This climate is determined by the influence of intertropical discontinuity, ITD, movement as well as the effect of relief. Maximum temperatures of up to 40 degrees Celsius can be recorded in April while minimum temperatures can be as low as 18 degrees Celsius between December and January. The mean monthly temperature ranges from 26.7 degrees Celsius to 27.8 degrees Celsius. Rainfall begins in April, progressing and reaching its peak in August/September and stopping most of the time in October. Average annual rainfall ranges between 998 mm and 1,262 mm. The cultural life of people in Mubi is linked to farming, animal rearing, milling, exploration and small-scale industries. Wante and Inalifo, 2014 cited Adio, 2004. Sampling and sample preparation. Selection of sample sites. A reconnaissance survey was conducted with the aim of identifying the common domestic water supply sources in Mubi North and areas with good representation of urbanization and agricultural activities. From the surveys conducted, 2 major wards in Mubi, Barama/Gipalma and Lokiwa, were selected for the study, from which 17 sampling points were selected. Common domestic water supply sources identified in Mubi include open wells, boreholes, and river points. The 17 sampling points earmarked were distributed such that every source identified and selected was apportioned 3 samples each except for River Mudra. Sample collection and analytical methodology. Sampling was done monthly over a period of 3 months from all 17 selected sampling points for all 3 common water supply sources identified. Simple grab samples from the rivers were collected 48 hours after a rain at commonly used water collection points. Open wells and the boreholes were purged so that the samples collected were representatives of groundwaters at the sampling locations. Purging of the boreholes was achieved using existing infrastructure where waters from the boreholes were pumped for a duration of 20 minutes before samples for analysis were collected. Purging and sampling of the open wells was achieved using a decontaminated baler, such that waters from the open wells were collected and discarded until the wells were considered stabilized and ready for sampling. Sampling procedure followed the protocol described in Triplet et al., 2006. All water samples were collected into 1 liter capacity acid-cleaned high-density polyethylene, HDPE, bottles with strict adherence to the sampling protocols described by Leo M. L. Nollet, 2007, Barcelona, 2014, and standard methods, APHA, AWWA, and WEF, 2017, and analyzed independently. Samples for BOT analyses were collected in specialized glassware. Replicate samples were collected from each sampling location as prescribed in Triplett et al., 2006. On-site analyses of temperature was done using a Celsius thermometer, pH, electrical conductivity, EC, and dissolved oxygen, DO, were conducted using Hatch-registered Senzion 156 portable multi-parameter. Turbidity was measured using a high 93703 portable microprocessor turbidity meter, HANA instruments. Before measurements, all equipment were adequately calibrated according to standards and all reagents used were of analytical grade. Water samples for laboratory analyses were collected with regard to protocols and transported to the Department of Animal Production Laboratory of Adamawa State University, ADSU, Mubi. Samples for metal analysis were preserved with 3 ml concentrated HNO3 per liter in the field to bring pH to less than 2, Begum, Mondal, Fairdas, Zafar, and Ali, 2014, David K. ETAL, 2011. The concentrations of major anions, SO42-, NO3-, Cl and PO43, total dissolved solids, TDS, total hardness, TH, and BOT in water samples were determined according to standard methods, APHA, AWWA, and WEF, 2017. The elemental concentrations, i.e. for Mg2+, Ca2+, in water samples were determined by an atomic absorption spectrophotometer AAS, Buck Scientific, VPG 210, following procedure as reported by David K. ETAL, 2011. Computation of Water Quality Index, WQI. This study adopted the Weighted Arithmetic Water Quality Index, WAQI, method because of its flexibility, in that it is suitable for use in assessing the quality for both groundwaters and surface waters, Engel and Jadhal, 2017. Inasmuch as the geometric aggregation method developed by Brown et al., 1973, was believed to be better than the arithmetic aggregation because it was considered to be more sensitive when a single variable exceeds the norm, it has its disadvantage in that if the value of one of the variables is close to 0, whatever the weighting of the variables, the WQI will tend to 0, Catchroud, Trillard, Keefi, and Jeberi, 2019. Therefore, the WAQI method has found more application by researchers, Ahmed, 2014, Imnisai and Aden, 2016, Engel and Jadhal, 2017, Oni and Faizakan, 2016, Ranabut, Singh, Chaurasia, and Bhatnagar, 2017, Tripathi and Shukla, 2017, Yogendra and Putaya, 2008. The method uses the most commonly measured water quality variables, such as temperature, pH, turbidity, dissolved oxygen, biochemical oxygen demand, total phosphates, nitrates etc. to classify the general water quality according to its degree of purity. For this study, 13 important water quality parameters were chosen and standards for drinking water quality as recommended by the World Health Organization, WHO, 2017, and Nigeria Industrial Standard, NIS, SUN, 2007, were adopted for reference, Table 2. The computation of the WQI, using WAQI method as proposed by Brown et al., 1972, was implemented using the following equations. Results and discussion. The results of the physicochemical parameters for the different samples of borehole water, open well water and river points obtained from Barama/Gipalma and Lokiwa as analyzed are presented in tables 4 and 5 respectively. The WHO guidelines, WHO, 2017, and the NIS guidelines, SUN, 2007, were recognized and used as recommending agencies standard in the water quality analysis and in the computations of the WQIs, Table 3. Analysis of physicochemical parameter. Temperature. All mean temperature values recorded for all the sources sampled from both Barama/Gipalma and Lokiwa locations fall below the standard set for maximum permissible water temperature by WHO based on palatability and aesthetic objectives, WHO, 2017. Mean temperature values of 28.28, 27.40, and 28.00, were recorded for borehole, open well and river points respectively at Barama/Gipalma. Similarly, mean temperature values at Lokiwa for borehole, open well and river Yedzaram were recorded as 28.00, 27.95, and 28.05, respectively. Driscoll, 2002, reported that water temperatures generally increase with the depth of wells. This fact explains why the temperatures of the boreholes were higher than those of the open wells, which are characteristically shallower. Temperature has been reported to affect the physical, chemical, and biological nature of the water. Kale, 2016. Sato, Hamamoto, Yuki, Oabo, and Moldrup, 2017, reported that a temperature increase of 7 can be responsible for changes in concentration of between 4% to 31% in magnesium, potassium, sodium and other important parameters in groundwater. Significant impacts induced on groundwater by increasing the temperature from 25.00 through to 60.00 has also been reported by Bont et al., 2013. They observed significant increase on pH, dissolved organic carbon, DOC, as B and F, with no consistent effects on Ca, Na, Fe, Mg, Cu, Zn, and Mn. The rivers are seasonal and hence they experience alternating flooding and drought situations. Characteristically, flow rates in such rivers are usually high and does not facilitate the effects of high water temperatures on the concentration of dew and the amount of dissolved materials. The alternating flooding and drought situations would however continually affect the water quality through dilution or concentration of dissolved substances respectively. Katrai and Tyagi, 2015, Pratham Ratna, Stianopko, and Kim, 2008, Tien et al., 2019, Van Vliet and Zwolsman, 2008. The temperature values obtained in the study were reported in a similar study by Oyem et al., 2014, and Maride and Ianu, 2016. Oyem et al., 2014, concluded that their values are consistent with temperatures prevailing and obtainable in the tropical belt. Turbidity. Turbidity in water refers to its degree of cloudiness or clarity. It relates to the ability of water to allow or impede the penetration of light due to the scattering effect of suspended particulate matter in the water. These suspended particulate matter may include clay, silt, fine organic and inorganic matter, or microorganisms. Abba, Abubakar, and Boyd, 2016, World Health Organization, 2017. For groundwater supplies, if turbidity is greater than 1 NTU, it is important to determine whether there is a potential risk for such water to cause health problems. Consequently, groundwaters with a turbidity greater than 1 NTU should be sampled for bacteria and nitrate. World Health Organization, 2017. The WHO standard for turbidity concerning potability of water is a value of not more than 5 NTU. All borehole samples analyzed for Barama/Gipalma and Lokiwa were observed to fall below the permissible maximum limit of 5 NTU, tables 4 and 5. Barama/Gipalma boreholes recorded a mean turbidity of 3.36 NTU while Lokiwa boreholes recorded a mean turbidity value of 1.82 NTU. The mean turbidity values recorded for open wells in Barama/Gipalma, 6.72 NTU, and Lokiwa, 8.52 NTU, and for rivers Mudra, 13.75 NTU, and Yedzaram, 13.89 NTU, did not meet the WHO/NIS standard for domestic water supply. Results obtained for turbidity in groundwater by the study is in agreement to Sali, Ankitawa, Ishaku, and Aminu, 2019, and Yada, Lamy, Usman, Bulama, and Zira, 2017. pH. The pH of water is a measurement of the degree of acidity or alkalinity in the water, or a measure of the concentration of hydrogen ion in water. The pH of water has significant impact on health and the environment. A pH of less than 6.5 inhibits the human body from the intake of vitamins and minerals, and when it exceeds 8.5 the water becomes caustic and irritating. Gupta, Pandey, and Hussain, 2017. The pH of the water samples analyzed are as recorded in tables 4 and 5. All results fall within the acceptable limits for pH requirements as set by WHO. The mean pH for boreholes in Barama/Gipalma recorded 7.76 and that of boreholes in Lokiwa recorded 7.23, River Mudra and Yedzaram recorded 7.80 and 8.15 respectively. Meanwhile, The open well samples recorded the highest mean values for pH, with the open wells in Barama/Gipalma recording pH of 8.20 while those in Lokiwa recorded pH of 8.70, Fig 2. The results obtained in the study are in agreement to those obtained by Alexander, 2008, Ishaku et al., 2012, Yusuf and Alkali, 2018, and Sali et al., 2019. Total dissolved solids. The amount of solids present in a water body is an important indicator of pollution from both organic and inorganic contaminants. The higher the concentrations of solids in a given water, the higher the degree of contamination irrespective of its source. Water containing high TDS is of inferior palatability and may produce unfavorable physiological reaction in the transient consumer. David K. et al., 2011, Kumar, Reddy, Jayavira, and Pradesh, 2016. Water with low TDS concentrations also tastes flat and insipid and therefore may also be unsuitable for drinking. Howladar et al., 2017. At TDS levels above 300 mg/L, taste and odor is amplified and TDS become noticeable to consumers, and as the concentration increases, water becomes increasingly unacceptable. High levels of TDS may aesthetically be unsatisfactory for bathing and washing. APHA et al., 2017. With reference to the results presented in Tables 4 and 5, the TDS values observed for the groundwater sources all fall within the acceptable limits for both WHO and NIS standards of less or equal to 500 mg/L for domestic supply. However, samples from the open wells having TDS values of 371.15 mg/L, Barama/Gipalma, and 448.48 mg/L, Lokiwa, Fig 2, may not make the first choice for a domestic supply source in the availability of alternatives due to possible amplification of taste and odor. Both river samples did not meet the standard concentration allowable in domestic supplies as stipulated by both WHO and NIS. Barama/Gipalma samples recorded mean TDS value of 579.82 mg/L while Lokiwa samples recorded mean TDS value of 548.91 mg/L. ONI and Fazakan, 2016, reported similar results for TDS in groundwater sampled in the vicinity of municipal waste dump sites in Ado-Ekiti, Nigeria. Yada et al., 2017, reported very low values for TDS in their study while Yusuf and Alkali, 2018, reported values greater than 1000 mg/L. Yusuf and Alkali, 2018, attributed the high TDS values to the impact of the heavy agricultural activities taking place in the vicinity of the water they sampled. Electrical conductivity. EC is a measure to the capacity of water to conduct electrical current. Its value is directly proportional to the concentration of salts dissolved in the water and hence to the TDS, Muride and Ianu, 2016. EC is also a function of the water temperature, that is, the higher the temperature, the higher the electrical conductivity would be. A temperature increase in a solution will cause a decrease in its viscosity with a consequent increase in the mobility of the ions in it. Barron and Ashton, 2007. Additionally, an increase in temperature may also cause an increase in the number of ions in solution due to dissociation of molecules. Consequently, a temperature rise of 1 degree Celsius in water may trigger a 2 to 3% increase in the EC of that water. Ichi-Osa, 2015. EC is closely related to the salinity in water and thus it is considered a good indicator of total salinity in water. Ichi-Osa, 2015, Rusadai, 2018. With reference to Tables 4 and 5, EC values that are acceptable with respect to the WHO standard are for the boreholes in Barama/Gipalma and Lokiwa. These sources recorded mean values of 396.45 mg/L and 432.22 mg/L respectively. The open wells and the river points all recorded mean values beyond the limit of acceptance as presented in Table 3. Interestingly, Yusuf and Alkali, 2018, reported similar values for EC. Total hardness. Total hardness in water is primarily due to the excess of Ca, Mg, and Fe salts, Beru, Tades, and Amori, 2013. It is an important water quality parameter whether the water is intended for domestic, industrial, or agricultural purpose. Hard water has been linked to, in addition to impacts stated by Gillam and et al., 2000, have tendency to influence mortality, in particular, cardiovascular mortality in addition to reproductive failure, cancer, and Alzheimer's disease, Sengupta, 2013. Total hardness recorded for the study in all groundwater, boreholes and open wells, and surface water, rivers, all lie within the permissible limits of 500 mg/L, as CACO 3, as per WHO standards. These results are consistent with similar studies conducted around Mubi, Alexander, 2008, Ishaku, Kaigama, and Onyeka, 2011. Magnesium and calcium. The desirable limits for magnesium and calcium for drinking water is 20 mg/L and 75 mg/L respectively according to NIS and WHO standards. Analyses on samples collected from all locations and from the three sources considered in the study reveal that all groundwater sources, boreholes and open wells, are acceptable for domestic use as per the standards concerned, while surface water samples failed for magnesium in all locations but are acceptable for calcium in all locations, tables 4 and 5. These values are consistent with those reported by Yatta et al., 2017, for calcium and Yanina, Yamta, Kaigama, and Bedason, 2017, for magnesium. Calcium-rich water is recommendable for drinking several times a day because it has the capacity to provide supplemental calcium and aids adequate hydration. However, it has an inhibitory effect on parathyroid hormone secretion and bone resorption causing stunted growth. Kotrovo J., Bartram J., 2009. Gilliland et al., 2000, and Sengupta, 2013, also reported on the ability of excess calcium concentrations to retard growth. The presence of calcium and magnesium in groundwater is linked to the leaching of geologic materials such as limestone, dolomites, gypsum, and anhydrites, although calcium ions are also derived from cation exchange process. Alaya, Sadie, Zemni, and Zargauni, 2014. Nitrates. The mean nitrate values for all samples were observed to meet the permissible limits of 50 mg/L set by WHO and NIS, tables 4 and 5. However, open well samples recorded higher concentrations of nitrates, 11.13 mg/L and 12.95 mg/L for Barama/Gipalma and Lokuwa respectively. Such high concentration of nitrates in water is a cause for concern as a nitrate concentrations of 10 mg/L and above poses a health threat to infants. Sharma and Kaur, 2017. Ward et al., 2018, reported that the risk of specific cancers, colorectal cancer, bladder and breast cancers, and birth defects is increased when nitrate is ingested under conditions that increase formation of N-nitroso compounds. Conversely, however, some recent scientific literatures indicate that high nitrates concentrations do actually have some beneficial effects on human health even though it remains an undesirable component because it is often accompanied by more dangerous constituents such as microorganisms and pesticides. D'Alessandro et al., 2012, El Hirondel and El Hirondel Jean-Louis, 2001. High concentrations of nitrate in water may indicate a possibility of anthropogenic impacts such as usage of nitrogen-based fertilizers, human-animal bodily wastes, and disposal of wastes in proximity to the sampling locations. D'Alessandro et al., 2012. The presence of nitrates in water samples is an indication of some bacterial and other biological activities. Illicini, El Azim, and A. Dowd, 2019. This is the reason why World Health Organization, 2017, advises sampling and investigation into nitrates and bacteria as suspects for turbidity higher than 1 NTU in groundwater. Sulphates. High values of sulphates concentrations above the standard of 100 mg/L, NIS, were observed for all locations and for all sources of domestic supplies sampled except the boreholes in Lokuwa. Sulphates are naturally occurring in water due to leaching of gypsum, barite, Epsom, and the dissolution of salts of sulfuric acid. Illicini et al., 2019, Sharma and Kaur, 2017. High concentrations of sulfate may result from the oxidation of pyrite and mine drainage and from human influences such as discharge of industrial wastes and domestic sewage. Gilambe, Alayu, and Manga, 2016. High concentrations of sulfate has been linked to some minor health concerns such as catharsis, dehydration and gastrointestinal irritation. Gilambe et al., 2016. Other health concerns raised by high concentrations of sulfate as reportedly found in literature by Sharma and Kaur, 2017, include renal failure and hyperthyroidism. Phosphates. Surface waters and groundwaters become contaminated from both natural and anthropogenic sources of phosphates. Natural sources of phosphorus in both surface and groundwater include atmospheric deposition, natural decomposition of rocks and minerals, weathering of soluble inorganic materials, decaying biomass, runoff, and sedimentation. Anthropogenic sources include fertilizers, wastewater and septic system effluent, animal wastes, detergents, industrial discharge, phosphate mining, drinking water treatment, forest fires, synthetic material development. Surface, Fadaran, Dlamini, and Maviso, 2008, Namati Varnas Fadarani, Murgafari, Ibrahimi, and Safianian, 2009. Phosphate is sorbed strongly onto solid phases, including Fe and Al oxides in soils, and P concentrations in recharging groundwater generally do not reflect the large amounts of P applied to agricultural fields. Bolk, 2002. Borehole and open well samples from Barama/Gipalma analyzed for phosphate recorded concentrations of 0.18 mg/L and 0.82 mg/L respectively. Both values are far below the maximum permissible concentration of 5 mg/L prescribed by the WHO standard. On the other hand, the mean value obtained for the river Mudjara was 6.25 mg/L, exceeding the maximum permissible limit for phosphate in drinking water as stipulated by the WHO standard. All samples analyzed for Lokiwa locations meet the standard of less than 5 mg/L concentration of phosphate. The mean values are 0.20 mg/L, 0.22 mg/L and 3.37 mg/L for borehole, open wells, and river Yezaram respectively. Phosphates do not have any significant impact on human health when they are naturally occurring in water. However, digestive problems, muscle damage, problem with breathing and kidney failure have been reported when high level of phosphates are consumed in drinking water. Fadaran et al., 2008, Gupta et al., 2017, Nyamangara, Jek, and Rurinda, 2013. Chlorides. Chloride is one of the major constituents of natural water and one of the most important parameter in assessing the water quality. Yogendra and Putaya, 2008. Very high concentrations of chlorides detected in water are commonly considered as important index of pollution and are therefore employed as tracers for groundwater contamination. D'Alessandro et al., 2012, Mugdo, Karna, and Bamaki, 2018. This study recorded very low values for chloride concentrations that are far below the maximum permissible concentration allowed by the WHO standard of 250 mg/L. With reference to Table 4 and Fig 1, 2, and 3, it can be seen that the mean chloride concentrations recorded for boreholes, open wells, and river points on River Mudjara are 7.62 mg/L, 12.04 mg/L and 6.80 mg/L respectively. Similarly for Lokiwa locations, boreholes, open wells, and river points on Yezaram recorded chloride concentrations of 9.19 mg/L, 12.86 mg/L and 6.96 mg/L respectively. Chloride concentrations in groundwater may result from saline water intrusion, application of de-icers, agricultural activities, domestic wastewater, industrial chemical, landfill leachates etc. Potability and Chakraborty, 2015, Ishaku, 2011. Considering results presented in Table 4 and 5, for both locations, the concentrations of chloride was higher in the open wells than those in the rivers. These values may be as a result of pollution from anthropogenic sources like agricultural chemicals, or leachates from pit latrines situated approximately to the open wells. Mugdo et al., 2018. The relatively lower concentrations of chloride in the river samples may be due to dilution effect. Nyamangara et al., 2013. Yusuf and Alkali, 2018, carried out a study on groundwater variation across a space in Mubi and obtained chloride concentrations in the groundwater in the range of 2 mg/L to 27 mg/L. Dissolved oxygen and biochemical oxygen demand. Results obtained for DEW for all samples and from all sources for all locations were above the minimum required DEW concentrations in drinking water as set by WHO. Similarly, the results obtained for BOD for all samples analyzed fall below the maximum permissible limit stipulated by WHO. However, considering the results presented in Tables 4 and 5 and illustrated in Fig 2 and 3, it can be seen that the mean concentrations of DEW in open wells from both Barama/Gipalma and Lokiwa, 7.89 mg/L and 7.85 mg/L respectively, are higher than the DEW concentrations in rivers Mudjara and Yezaram, 6.90 mg/L and 6.88 mg/L, even though surface waters are prone to more oxygenation. BOD is a function of the amount of organic matter present in a particular water environment. Hence the value of BOD is an indication of the amount of oxygen required by microorganisms present in the water environment to decompose the organic matter in it. Consequently, a higher BOD value would indicate a higher amount of polluting biodegradables in water, which invariably would require higher amounts of DO for its stabilization. On the other hand, low levels of BOD will indicate low levels of biodegradable materials, and hence higher amounts of DO may be available in the water environment. This may explain the inverse relationship exhibited in the values for DO and BOD, Fig 2 and 3, for the open well sources and the river sources. The mean BOD values recorded were 1.45 mg/L for open wells in Barama/Gipalma and 0.88 mg/L for open wells in Lokiwa. DO values were 7.89 mg/L and 7.85 mg/L for open wells in Barama/Gipalma and Lokiwa respectively. Similarly, the results obtained for the surface waters are, BOD, 2.67 and 2.65 mg/L for river samples in Barama/Gipalma and Lokiwa respectively, DO, 6.90 and 6.88 mg/L for the respective locations. Water Quality Index. This study considered 13 important water quality parameters to establish the water quality index for the sources and locations sampled within Mubi. These parameters were selected to reflect the common activities around the study area and the possible pollution indicators from such. Parameters include turbidity, pH, TDS, EC, TH, Mg, Ca, nitrates, sulphates, phosphate, chlorides, DO and BOD. The results obtained for the WQI from the different sources are as presented in Tables 6 to 11 and summarized in Fig 4. Similarly, the water quality and the grades for all locations are summarized in Table 12. The results of WQIs computed for the borehole sources showed that on average, boreholes waters from the two locations, Barama/Gipalma and Lokiwa, are of good quality. The values obtained fall within the range of WQI level of 26 to 50 and grade B, Table 2, describing drinking water of good quality. However, boreholes from Lokiwa have a better quality rating, WQI equals 31, than Barama, WQI equals 45, with reference to Figure 4. This result may be attributed to the higher values recorded in samples from Barama/Gipalma for turbidity, TH, 2+, pH, 2+, and 42 over Lokiwa samples as illustrated in Fig 1. For the open well samples, results obtained from the computation of the WQIs were 70 and 78 for Barama/Gipalma and Lokiwa respectively. These results fall within the ranges of 51 to 75 and 76 to 100 for Barama/Gipalma and Lokiwa respectively. These therefore describe that the water quality statuses for Barama/Gipalma and Lokiwa are, poor water quality, grade C, and very poor water quality, grade D, respectively. The high concentrations for, 3 pH, turbidity, TDS, EC and TH could be responsible for the higher WQI obtained for the open wells in Lokiwa as seen from Fig 2. WQI's results obtained for the river points sampled from the river Yedzaram along its reach within Lokiwa, WQI equals 123, and river Mudra within its reach along Barama/Gipalma, WQI equals 116, indicate that the river reaches considered are having waters unsuitable for drinking purpose. The river points for both Barama/Gipalma and Lokiwa have a grading of E, the least possible for Vaki method. Conclusion. The quality and suitability of some domestic water supply sources in Mubi North were determined through physicochemical analysis and WQI computations. Physicochemical analysis showed that the pH, TH, calcium, nitrates, chloride, DO, and BOD for all samples from all sources in both Barama/Gipalma and Lokiwa met the limits of acceptability by WHO and NIS. Turbidity and EC failed for open wells and river points in all locations, while TDS and magnesium met the standards in boreholes and open wells but failed in all river samples. Phosphate values as analyzed were all within permissible limit for all samples except river Mudra, which recorded a mean of 6.25 mg/L as against the 5 mg/L stipulated by WHO. The concentrations of sulphates in all samples failed the maximum permissible values stipulated by NIS except for the borehole in Barama/Gipalma. Based on the WQI computations, the water quality and suitability of sources based on the Vaki are, good water quality for BBH and LBH both having grade B, poor water quality for BAU grade C, very poor water quality for low grade D, and unsuitable for drinking grade E for both river points. Even though most of the parameters tested were found to fall within permissible limits of concentrations based on the standards agencies adopted, however, the weighted arithmetic water quality index computations as summarized on Table 12 and illustrated on Fig 4 indicate on average a poor water quality status for the study area. This outcome is understandably possible since the combined effects of the tested parameters were taken into consideration by the WQI model employed.